All right, welcome back. Hold on, I used one last hour that was really dumb. Yeah, what's good, Gucci gang? Today, we are going to come back to this. Now, thank you, Sabrian, for having a better memory than I. As we look at this, I have a circle on the board. I'm going to claim I'm using this circle to represent a sphere instead, or a close to sphere. This is the what? What have we been talking about? We've been talking about the planet, and specifically, the first section was the wind. Now, with the winds, do you want me, I'm going to draw our planet and remind ourselves of the winds, because you can't talk about Ekman transport and the Ekman layer and the Ekman spiral without talking about the winds as well. But I think that we can make sense of what's happening with this. Okay, here is this lovely line called the equator. And I'm going to try to make it a little bit more lovely. So, I am not outlining your notes in the same way I normally do, because you should have some. But we're going to hit the ideas here because they're odd when you just read them from the text if you don't have any other basis for it. So this, if I were looking at it and if I were labeling it as notes, this is like 5.2 prep work is what I'm looking at. So I'm going to look at one specific zone right now. Let's look at this zone on our planet, which if this is the first mark, I know it's not to scale, but do you guys agree that that could be 30 degrees? Okay. Without going into crazy detail, air gets hot. Right here, air gets hot. Air does what? Air goes up. Okay, air goes up, leaves space. Air must come down or up to get there, depending on which side of the planet you're in. So we get winds coming down like this. That's my convection current. They have specific names, but it's not our focus of it. Cool. Do you guys agree that the wind travels south? Like if I look here and I say, hey, here's this wind that air comes up, air comes down, and then we know some of it winds up going like this. But if I'm only looking right here, some of it just comes back down like this. Which means if we were to look at just the planet, the wind wants to do this. Straight toward the equator, right? However, the planet's doing something that messes with this. The Coriolis effect is what we call it. The Coriolis effect is that path there changing because the Earth is constantly doing what? Spins. Now, when we talk about deflection, the language gets weird. And it gets even weird as you read it in the textbook because it's kind of ambiguous unless you're really specific about it. The other day in class, I like this language, but it's maybe another way to word it with Ekman stuff makes it easier. That wind that blows south from 30 north toward the equator, that's the trade winds. These are the northern trade winds right here. Which way do they deflect? So even just that question, if I'm going to draw this, I know that it's going to wind up curved. Should it curve to the west or should it curve to the east? It curves to the west. So we have this wind that goes south that deflects this direction. Okay, now I like to use to the west because if I'm in the southern hemisphere at 30 south and I look at the same thing, this now moves north toward the equator and it also deflects. To the what? To the west. Okay, this is what's responsible for our trade winds blowing. Now, we're going to take one further step forward with this. I prefer saying it deflects to the west. We're going to switch and I'm going to offer just slightly different language. Imagine you're on the wind, or you are the wind if you want to get real hippy-dippy with it. If you were walking and you're following the same direction as that arrow, from your perspective, which way do you turn? Here's a person walking. In the northern hemisphere, right here, they turn. What direction did they turn? Don't use east or west. Right. They turned to the right. In the northern hemisphere, they turned right. You guys agree with that? How about your southern counterpart? They turned left. And this is why I prefer the language of east or west over this, because then you don't even have to worry about what direction. Okay. However, this language is helpful if we start somewhere else. I know the air here goes upward, right? On this second little piece. These are my westerlies. Okay. Specifically, the air pushes up, and in this section, it deflects where? Does it deflect to the west? It goes to the east. Now, this is how it deflects here. We already have that horizontal speed, and when I go up, the planet's moving slower because of the size of the planet. It gets deflected that way. If you look at this language now doesn't let me rephrase that in a way that makes sense. The language of east and west feels funny now when I talk about this. However, if we look at this path, on that second part, the westerlies, if you were the wind, which way did you just turn as you were going? Did you deflect to the right or to the left on your path? Up here. You've gone to the right. Which way did we deflect before? To the right, because remember, we're looking from the perspective. The person's walking, and they turn to the right. The person is walking, and they turn to the right. Saying right in this situation allows us to account for both directions. Okay, there's weirdness with the language. Is this clear what I've said? Follow the arrow. Imagine you're walking that way. You're going to turn to the right in the northern hemisphere. So, to prep this then, I would encourage you should make this statement. In northern hemisphere, and this is all the prep work for this, just to make sense of the Ekman stuff. I'm going to call it a hemi. We turn what direction? We deflect to the right. Now, notice I'm not saying east or west because we're looking from the wind's perspective. To the right. Okay, that's our first little piece. In the southern hemisphere, if I were to look maybe at the other direction, I'm going to go, how do I want to do this here? We'll do this one. Same thing, I know that the air winds up pushing out like this. What way does this air deflect? Right here is the one I just added. Should my path be there or there? 1 or 2? 1 or 2? 1. I agree. Okay, now, same idea. Notice, if you're in the southern hemisphere and you're the wind and you're walking, you get pushed to the left if you're going north. If you're here and you're walking, you get pushed to the left. In this situation, it makes sense to use left and right compared to east and west because of these wonky changes in direction. Okay, if you want the other statement, I would say in southern hemisphere, we deflect where? South, left. Okay, that basic idea allows us to have the language needed to really lock in this Ekman idea, I think. Cool. Now, on the surface of our Earth, there's a lot of water. Like 70% of our surface is water. Okay, there's also a lot of air that interacts with that water. We've already seen that. If there's a lot of ocean and there's a lot of air, is there a lot of wind on the ocean? Do you think there's a lot of wind in the ocean? Not in, but on? For sure. Like, we use advantage of that as people, right? Okay, here's what I want you to imagine. If we had, and you don't have to sketch, this is just me thinking. You guys have all either played in a bathtub or in a pool, I imagine. You ever felt a little crazy and done that thing where you make a wave by dragging your hand under the water? Everybody has, right? And if you've never done it, you should. It's interesting. So let's just do a little thought experiment here. Let's say that I have this lovely bucket of water. You do not have to draw. This is just me thinking. Okay, and I had a ping pong ball sitting on top, and then I don't know how I worked out the densities, but I got another ping pong ball to sit here, like a little bit below the water, and another one to sit below the water here. Okay, we just have a small pail of water. I'm good with that. Now, whether it's wind caused by my breath, or I'm going to use a blow dryer in my head, that's the first thing that I think of. If I were to have a blow dryer, it's getting ready. It's got the old school one with all the coolers and stuff. Pretty sweet blow dryer. Okay, as we look at it, if I were to blow wind here, will the top ball move? Okay, I agree. Now, we don't know the real scale of this. Will ball number 2 also move? So, but here's what I want us to think of. I'm going to use what's called a vector. How many of you guys have taken geometry? Or are currently? Okay, what's a vector? You guys ever seen this that doesn't go forever and it just stops there? That's a vector. Cool. So I'm going to use vectors to represent. That sounded really dismissive. That tone was not intentional if it sounded like I was being judgy. I wasn't. Okay, check it out. This ball moves, and I'm going to say it moves with this amount of velocity. There's no real number to it, but that amount. The ball below, will it move? I think so. Now, it depends on the depth, obviously. But if I move this ball, I think that it's reasonable to say the water underneath of it will also move, right? And do you agree that water, even though there's not a ton of it, there's a little bit of drag. Water drags on water, which means there's a little bit of drag, so I'm going to lose it. Will this ball here be moving the exact same speed, faster or slower? Slower. Now, assuming the depth is at a value that I can actually do this with, this last ball might also move. Now, there will be a point where it doesn't anymore, but if we assume that it would move because the water above it's moving, more, less, or the same? And I get less movement as I go until I don't get any more. Everybody okay with that idea? What we have just hit on are what we're going to classify as our Ekman layers. Now, specifically, the Ekman layer is that very top one. And it's named after a oceanographer. I can't remember his first name. Anybody care? He would be really hurt if he heard that answer, just for the record. Was it really George, or is that just a guess? I have no idea what his name is. They must tell it somewhere. Dr. Ekman. I don't know. I couldn't find it. Okay, so this idea, as long as you're comfortable with saying the top of the water moves more than the water underneath of it, which also does move, we have everything that we need for Ekman. So check it out. As we start looking at this, if you have a definition for Ekman transport or anything to do with it, what is it? Yeah, what's Ekman transport? So here's my challenge. Everybody probably wrote it down. Assuming that you had it, you probably wrote down exactly what's in the book, which I totally get it. That's okay. But here's what I'm going to suggest. If you write something down and have no idea what it means, Dwayne, do you agree that it was a waste of time? If I write something down and have no clue what it means, was that valuable? No, I probably shouldn't have even written it down. But, again, everything, I just feel like I'm being really aggressive with you guys. I hope it doesn't seem like your faces agree with that. Talk with your neighbors. If you wrote it down, that's cool. I want you to be able to tell me what is Ekman transport. Give me a basic overview of the whole thing. You wrote it all down, but I don't know if you understood what you wrote. That's the question. What's up? We'll check Monday. We should we'll check Monday. Like that. I might grab the layer below there in my creates a new, unfortunately. Yeah. Okay. Which booth is yours? Okay. It's like the cleanest one, like for real. There's nothing in there. Okay. All right. I'm going to randomly pick somebody. Hopefully your group. You guys had enough time to discuss it. Anybody realize in this, and there's no, I'm not trying to get you. Anybody realize you wrote it down but you have no idea what it is? Guilty. Yep, that happens. Okay, so before I just make somebody try to explain it in front of everybody, anybody want to try to volunteer what it is? Okay, for this, the explanation to it's a little bit bigger, but I'm going to make the following claim. Ekman transport is just the movement of water perpendicular to the wind. 90 degrees to the wind. That's what it is. And it turns out that it happens in a spiral as you move down into depths. And that idea maybe doesn't mean a ton. I know that the first Ekman layer is roughly 20 to 45 degrees with the wind. Okay, and the explanation for that, they just say it. They never really explain it in here, which kind of bothers me. But here we are. That's my job. So, as we look at it, here's what I want us to think about. And my pictures, some of them are awesome. They're not all awesome. I'm going to do a little bit tiny different picture than they make. So, if we're looking at Ekman transport, overall it's the net movement of the water caused by the wind and combination of wind and Coriolis effect and friction, and there's a whole lot of moving pieces to this. The first main idea, I believe, in your book is that Ekman transport. So here we go. I'm just going to say Ekman. Now, where this was really discovered, don't know, I don't recall the year, but what Ekman realized is he saw ice floating and he was somewhere cold. He saw ice moving and he knew that the wind was always blowing because he's on the ocean. and he realized that the ice moved in a little bit different direction than the wind, which is weird, because if I'm on the ocean, I'm blowing wind constantly that way, it seems really counterintuitive for something sitting on top of the water to go that way instead. Like, it seems weird, doesn't it? Like, just even thinking about it, should go the direction of the wind. Now, the thing that Ekman realized is that not only is the wind blowing and the water's moving because of it, but the Earth is still doing what? It's still spinning. So there must be a little bit of the Coriolis effect that acts on the water as well as it acts on the wind. So, my picture, you do not have to be super artistic with it. I'm not super artistic, but check it out. We have wind. And as we're looking at it, if I have it getting smaller away from me, why would it possibly do that? I'm being crazy with my pictures because it helped me make sense of it. Why would it be smaller over there? That's right. I'm using 1-point perspective to make sure that there's a clear depth to my arrow. Okay, here's the wind blowing. And I'm doing it three-dimensional for a very specific reason. It's not because I want to show off that I can draw 3 dimensions. Okay, I thought that was funny, but all right. Cool. Now, beyond this, it gets better. It gets so much better. We are going to think of a water table existing by this wind. Now, you don't have to draw a big fancy 3-dimensional picture. I had to make sense of it in my head as a way to make this connect with everybody. Here's a bunch of water, and I'm not going to add anything else to it yet. I just have a big cube of water hanging out right now. Now, in this water, there are a variety of depths. Like, obviously, water is a certain amount of deep. Cool. So, beyond this, I also have on mine a lovely different point perspective showing the depth increasing. Because check it out, I have this pole that's going to help me kind of orient myself with where the directions are pointing. Now, for this, the book never mentioned this, and it drives me bonkers. Let's assume, and we need to write this, we're going to assume that we're in the northern hemisphere right now. If you'd rather do south, we could, but we'd have to redraw the picture, so we're going to do north. Okay, I want a very clear note. Your picture doesn't have to be perfect, but we need to say northern hemisphere. Okay, if it's not black, I don't want you to draw it, okay? The book does not specify. I don't think that. Does it say that this is the northern hemisphere as they're looking at it? So equatorial upwelling, it might talk about the specific thing, and then they even use it an example without ever specifying it. They use an example from the southern hemisphere as well to show the exact opposite, but they never specify the southern hemisphere. Not that I noticed. Like, they do mention it, but if it's not black, I don't want you to draw it, okay? So check this out. Assuming the Earth wasn't spinning, again, do not draw this one. If I'm on the very surface, very top of the water, we would anticipate that the particle moves like this. Now, we did a little bit of front loading to start this a few minutes ago. In the northern hemisphere, if you were in a vector, like we've just drawn on the board, which way would your path deflect? If you're in the northern hemisphere, it deflects to the right, regardless of whether you're walking north or south. Now, what they do, and you don't have to draw both of them, but what it ultimately winds up doing is that this might be the vector that we get instead. Now, this isn't truly a vector because now all of a sudden it's curved, but check this out. If I just identified that spot right there, and I'm just going to eyeball it to the best of my ability, and I go back to my black instead, and I just draw a single vector going, it started and ended at the same spot. Now, that is not quite parallel to the wind. It has been deflected to the right. I just haven't showed the curve of that deflection. I just said it starts here and it ends here and I draw a straight line. Is that okay with you guys? Doesn't look like it for everybody. So check it out. I'll add the red one here. The wind wants to push it this way. But I know that the path, because I'm going to the right, will deflect like this. So all I've done was I marked off the spot and then I just drew a single straight line. Okay. This right here on the very surface of our water is the Ekman layer. Now, the wind has deflected, or sorry, the water has deflected a little bit, and I should have drawn this parallel, but that's okay. If there's the original direction, your book specifies this. What angle did we just form?
45.
Roughly 45. Realistically, it's between 20 and 45, but that's the 45-degree angle. It's the deflection caused by Coriolis. Okay, With that, here's where we have to start thinking a little bit further. This is the Ekman layer. It's this top layer that deflects just a little bit away from the wind. Okay, if we go down a little bit more, we're no longer thinking about the wind. Is there conceivably a particle, and I just need a little bit less bold, is there another depth somewhere in here that's a little bit deeper? And its direction, initially at least, wants to go exactly the same. I'm going to do this in red. Its initial direction wants to go the exact same as this because the water here is what's causing this water to move. Everybody okay with that? The water at this next depth down moves because the water above it moved. Now, is this still on planet Earth? Like, it's in the water on Earth. So yes, that I wasn't trying to give you a trick question. This thing is in the northern hemisphere and I'm traveling. And my path, if I'm traveling in the northern hemisphere, due to the rotation of the Earth, it's going to deflect somehow. How will it deflect? To the right or to the left in the northern hemisphere? So I'm going to do the same thing. This looks to me that it would be parallel, but I know that in reality, the Coriolis effect causes this to also deflect. But I'm not doing it from the wind, I'm doing it from the water one step above. Okay, if I mark this point and said this is where the water really wound up, I now get this. And I'm going to draw my black line again. If I go a certain depth, I know that the water deflected 45 degrees from the wind. This is a weird sounding question, but what do you think the deflection of the water from the water wound up being? Maybe 20, maybe like somewhere between 20 and 45, I would argue. Could we repeat this again? If I go down deeper, it's the movement of this water that causes this water to move. It wants to be parallel, and I'll do the same thing. I would not jot the red down unless you need it. It wants to be parallel with that black path, because that's the way that the water actually moved. But in the northern hemisphere, this is still water that's still moving and the Earth still spins. This red path should deflect how? To the right. So same thing. This layer caused this layer to move, and as it moves due to the Coriolis effect, it deflects to the right again. This is where my three-dimensional drawings get kind of rough. And I wish I'd done this with all of them, but I didn't want to take the time. This pushes out further still. Now, if we looked at it, what we see happening, and I don't know if I can show it on here. If I went another step further, and this is just hard to draw, I think the next one down is going to come out, and it's going to be coming out toward me. This does not really look like it's out toward, well, maybe it does. Does that look like it's out toward us? And then again, if I go a little bit deeper, now it's coming out toward us, but a little bit more to the left. And then a little bit deeper, it's coming out this way. And eventually we wind up seeing like it almost exactly turns around. It's almost like from the depth, we get a nice, lovely spiral that shows up. Named after whom? So what do you think we call this wonderful spiral within the water column as we move depth? There's too many words to make that work nicely. What spiral is this? It is the Ekman spiral of the different layers acting on the next layer down with this shift in Coriolis. Okay, as we go through here, this is what's really happening. Now, if we had to take an average of a bunch of stuff, do you guys know how to do that? How do you take an average? Like we're going to say 20 people in here. Let's say there's 20 people in here and you all take a test or a quiz and I give you the average. How do I get it? I add them all up and then I do what? I divide by the number. Now, check it out. These are a little bit different and we're not doing like fancy vector math, but we're going to make sense of how the math works, not actually the computations. Does this have a lot of size and direction? Like right now, if I thought of my arm as a vector, it's some amount of length and it's going that direction, which is a combination in 3 dimensions of left, right, or up, down, and in and out, right? Okay, if I take this and I add it up with this, change in direction, change in size. And I did it more and more and more, and I got a bunch of them. Could we take the average direction that it pushes? Like, and I know that's weird, but check it out. If I said that this, and this is going to be in red, if I said here's something that pushes that hard, so just that length, that way, and something that pushes this hard, the exact same size, the opposite direction, what are they going to average out at? Would you agree it's 0 because they just cancel each other? Now, if we look at the spiral here, and I just draw it in a single one-dimension thing, let's say I'm looking down at it. I have a long vector that points this way, and then a little lower I have a smaller vector points like this, and I'm looking down at this right now, okay? And we'll start there. Then another shorter one that points that direction, shorter one that points that direction, shorter one that points that direction. If I said average these, and again, I'm looking straight down at it, so I'm viewing it, looking straight down at the circle. What average direction do these go? Everybody agree it's going to be to the right? Like, we have, this is the overall average of this, right? So check this out. Turns out that if we did exactly this on our picture, you do not have to do yours fancy, but I'm going to because I took the time to learn how to do it. If I take this whole idea and all of a sudden, just for fun, we add this wonderful arrow up here. It's almost like we have this whole column of water now being pushed with what relation to the wind? Oh my gosh, it's like that whole column of water on average is moving perpendicularly at 90 degrees to the wind because I've added up all these different angles pointing off. If that is the direction that it goes perpendicular to the wind, it means all the stuff in the water is going to ultimately move which direction? So in this, it looks like it's to the right. I would agree with that. But away from the wind perpendicular to it. This is called what? This is your Ekman transport. It's the net movement of all the water based on all the different angles and strengths that are being pushed and moved by the water column. Like, it's a really big convoluted explanation. This, I hope, makes more sense than it did, 20 minutes ago before we started talking about it. It's a lot of different ideas kind of tied together. This is Ekman. This is his big discovery, which is huge because it turns out that if you want to do things like aquaculture or anything meaningful with our oceans, like making a ton of money getting crabbed because you need to know where to fish, whatever the case is, this is it. Okay, in general, the net movement is all the way over. This is the picture of Ekman transport. Feel okay, feel terrible. All right, now, I don't know how hardcore your guys' notes are. I just barely glanced at them. As long as you remember each thing goes to the right in the northern hemisphere, how would this picture look if we did it in the southern hemisphere? It would just flip completely backward. It would deflect to the left a lot at the top, and then each layer, it'd just be all the way to the left afterward. Cool. So, looking at this, we get this huge idea. Turns out that this happens with a ton of water all over the planet. Now, it doesn't happen constantly, but there are a couple big ideas that we should get out of it. I did not love the picture that they gave us. Now, theoretically, I'm going to come back and I'm going to look back at our planet. So here's our planet. If I say that, hey, let's just look at the water in general, as we get near the equator, it's essentially going parallel to the equator like this. Okay, which means transport's happening what way? Those are way too bold. They're not going to make a good picture. Did I lose you guys in saying that water generally moves this direction? Or the winds generally move that direction? Okay. When I do that, in the northern hemisphere, Ekman transport would happen to the what of this arrow? Which way do we deflect in the northern hemisphere? Everybody agree that here's my Ekman transport happening? Okay, what about in the southern hemisphere? To the left, which would push this south. Here's all my nutrients, all my water being moved via this Ekman transport. Now, just like we saw with the wind, if you have a ton of water right here that then moves up, like, this, what did it leave behind? I mean, yes, you're not wrong. Let me rephrase this. Did I leave a void where there used to be a bunch of water? It's not the same water that is there anymore. There is still water. Where did that water have to come from, you think? So maybe it could have come from down here, but Ekman is pushing it away, isn't it? So I think it seems reasonable that maybe, and I'm using colors not really specifically, this winds up pushing the water here, which winds up pushing the water here, which pushes, and we get this whole big circular cycle just like we did with the air. Because air is a fluid, just like water. we get the same big cycles on the surface of the planet that we did when we talked about our convection currents. Okay, when we do that, turns out if they're big enough and strong enough, they dictate pretty much the entire currents moving around our ocean. These big circular cycles caused by this Ekman transport and the winds that are blowing, it has a name. You're probably going to mispronounce it. I don't remember its phonetic. It starts with a G. This is a gyre. This is a gyre, not a gyre. This is a gyre. Okay, when we talk about our gyres, we get a lot of them on our planet. And you guys get this picture that is included. We're going to have to pause here in about 2 minutes. Here's the picture that's in your text. There is a lot going on. Now, there, luckily for us, is a legend. They say, hey, check it out. We have cold water, which, lo and behold, away from the equator. So we do get a little bit of the convection with heat and difference in temperature happening as well. But check it out. We have our winds blowing. So the winds are these yellow dots. So here's our trade winds coming in, and they're getting parallel with the surface as we get nearer. Okay, upwelling starts occurring and moving all the water up that then cools down. And for that, along with Ekman transport occurring, we get these big gyres occurring. Notice, in the northern hemisphere, they turn clockwise. In the southern hemisphere, they turn counterclockwise, which is that same deflecting due to Coriolis idea. Big gyres wind up telling us how the ocean's going to move. Okay, beyond this, we need to talk about upwelling also, but I'm going to hold that until Monday. Sweet. Okay, in general, I know the answer I want, but I don't want you to answer just what I want. Like, legitimately, do you feel better about Ekman transport now than you did? Yeah. Really complex idea. Still really complex, but so much easier if we chat about it. Okay, today we're going to go over to the hatchery. We're going to do 2 big things today. First big one is we can take the trays completely out of the incubator. There's still some fish or alevin swimming around in them. Our job is to get the alevin out of the trays that are there into the raceway. We also need to vacuum the raceway, which, what do you think we might run the risk of? You could possibly suck up a fish. So we are going to go ahead and zip tie to the end of our vacuums some wonderful mesh to make sure that if we do vacuum up a fish, all we have to do is kill the vacuum and he can swim away, or she can swim away. I don't really care how they identify. Cool. All right. We'll then turn off the incubator water feed, and we will start, we won't finish, cleaning all those trays that came out of it and the incubator itself. Cool? World Star. If you need to go grab a jacket or whatever, you can, but we should have enough jobs for everybody. Do not feel obligated to bring stuff.